Okay, so today we're going to talk about avian flight. This is chapter 5 in your book, which goes over the mechanics underlying lift and drag, flight efficiency, the morphology of the wing and how that affects flight, and flight stability. So, one of the first things that your book talks about is how lift is generated, and it gives you a sort of general model to start of and start thinking about how lift is generated, and then it goes into more specifics. So I've done the same thing here. In this image, on the left here would be where the head of the bird is, and on the right then it's the tail of the bird. Here, this is the cross-sectional area of the wing, or this is the straight line distance. Here would be the wing chord. And what we have is free stream velocity. That's the air coming into the wing, reaching the wing, and then you see that the wing deflects the air along the shape of the wing. This shape is called an airfoil. So if you hear me say airfoil, I'm referring to this. The wing is what I'm referring to, this shape. And so the air is deflected along the upper surface of the airfoil, and the velocity of the free stream velocity is pulled downward. In other words, we induce a velocity on the air over the wing in a downward direction. As we know from Newton's laws, if we recall physics, um, any force in one direction generates an equal and opposite force in the other direction. So a really simple way of thinking about the production of lift is in thinking about the fact that any downward induced velocity has to generate a force in the other direction, which is up, and that force is what generates lift. The nuances of that are a bit more technical, but let's see if we can understand those. Here we have free stream velocity coming in, and then we have to understand what some of these arrows represent. So you have purple arrows, and you see the purple arrows are different colors. The purple arrows are the local flow. That's the flow right around the airfoil, right around the wing. And you see those arrows are different magnitudes. In other words, they're different lengths. The ones above the wing are bigger arrows, and the ones below the wing are much smaller. The That is because the velocity of the free stream velocity gets sped up. It gets accelerated as the free stream velocity hits the wing and it gets pulled down along the airfoil contour of the upper part of the wing. And so those upper arrows are big because the air gets accelerated. On the underside, those are very small arrows because the opposite happens. The air loses velocity on the underside of the wing. And so you have a difference in the amount of velocity of the air on the top surface and bottom surface of the wing. The red arrows here represent the difference when you take the local flow and subtract the free stream velocity. And so we can do a really simple example of this is if free stream velocity is 10 miles an hour, it hits this wing and it gets accelerated to 11 miles an hour over the top of the wing, then the magnitude of this arrow would be 1. It's 11 minus 10, 1 mile an hour difference. In this case, that's the net acceleration occurring. And then down here, we have the same thing, but let's say it gets slowed from, let's say it's going 10 miles an hour and it gets slowed down to 9 miles an hour. Well, now it's not 1, right? It's local flow minus free stream velocity. It's 9 minus 10 is negative 1. The net flow is actually in the opposite direction. So what this does, that's why this red arrow is facing the other direction, right? Every other arrow on here is facing uh, um, to the right of the image because all the air is flowing in that direction. But when you take the net here, when you take the net velocity here, you've lost velocity, and net flow is actually in the other direction. What this creates is something called bound circulation. And you can think of this like a vortex of air constantly circling the wing. And that vortex of air is created by differences in pressure. And it is that pressure that creates lift. So that is how an airfoil creates lift. If you look at airfoil physics that you might see explained for something like an airplane, it's exactly the same mechanism. You can go into a lot more detail about this, and if you're interested in, say, engineering or something like that, and you work on airplanes, this would be something that would be very important to do. For us, I think this is an adequate understanding of how this circumstance arises. Differences in the velocity above and below the wing cause this bound circulation, and differences in pressure above and below the wing ultimately result in lift. Okay. And so I guess I should say here, you can see you have a low pressure, a low static pressure specifically, above the wing, and a higher pressure below the wing, right? That's the lift. Okay. One of the major factors contributing to how much lift can be generated with an airfoil is how long the airfoil is. So we can measure this in birds with wingspan, which is just the distance between the tips of the wings. If birds want greater lift, all they have to do is stretch out their wings. And what they get is they get greater surface area. They're capturing more of that pressure differential created by bound circulation. And by having that greater amount of high pressure underneath the wing, they can get more lift. And so when you see birds with their wings fully outstretched like that, that's what they're doing, is they're capturing bound circulation to generate lots of lift. Birds have to modify that lift, though, as they fly. They don't always want to just keep generating maximal lift. And so the way they do that is, one way is by tucking in the wings. If you tuck in the wings, you have less lift because you have less total surface area for the lift to be generated from. Another really important factor in determining how the wing functions is something called camber. Camber is sort of a description of the curvature of the wing. If the wing chord is the flat line distance from the front leading edge of the wing back to the tips of the remiges, the wing camber is a measure of the arc of the wing over that wing chord. You could have a very arced wing like this, or you could have a very flat wing that has no camber at all. The more camber you have, the more arc you have, the more lift you can produce. There obviously is some optimal balance between camber and no camber or extreme camber. There's a middle ground that is like an efficient and appropriate point of camber. But a lot of that depends. Well, the best camber for a wing depends a lot on what species of bird you are and how you live. So this is a place where you can directly tie wing morphology to bird natural history, and we're going to see several examples of that over the next few slides. And I will show you in just a slide or two here some of these ideas. So as the bird is flying or gliding, whatever, or soaring through the air, the amount of lift generated is going to depend on how the bird angles its wing in relation to the incoming free stream velocity. So we could have a wing that's very close to or even parallel with the free stream velocity. If we did that, we would generate uh, relatively not a lot of lift, but we'd also generate very little drag. Now, we haven't talked about drag yet, but drag's very important. Drag is any force that opposes the direction of travel. There are different types of drag. There's induced drag. That's the drag that's caused by generating induced velocity. And then there's also pressure drag, which is the cost of displacing air around the wing. And then there's friction drag, which is the drag that's caused by the adhesion of air molecules to the wing as the air travels over the wing. So there's different types of drag, but all of them are doing the same thing. They are acting as a force opposing the direction of travel. So again, here, when the wing chord is more or less in line with free stream velocity, we don't have very much drag, and that's a good thing because you have to fight against that drag to move in a direction you want to move. But it also doesn't generate as much lift as it would if you tilt it. And so if you tilt the wing a bit, you actually get a bit of a trade-off here where you can get very high lift. Sorry, I keep looking at the wrong screen. You can get very high lift, but it gives some more drag as a result because you are no longer, here the wing chord's no longer parallel with free stream velocity or close to parallel. It's starting to tilt at a harsher angle to the free stream velocity. But if you can generate high lift at the cost of only moderate drag, that's optimum. That's not you're generating a lot more lift for a relatively not that much more cost. As you continue to increase this angle, this is the angle of attack again. As you increase that angle of attack, there is a point at which you get way too much drag. And it can be so extreme that it will actually stall flight entirely if you depending on how severe the angle is. And at that point, it becomes really difficult to attempt to overcome this drag. It becomes very inefficient. And obviously, that is a poor approach to flight. That's not what you want, a highly inefficient flight. So the optimum angle is somewhere between parallel with free stream velocity and perpendicular to free stream velocity. It's something in between. It's something like what you see in picture B here. So some examples of how we can tie those particular concepts to avian natural history. First, birds can modify their camber. Many birds, most birds in fact, modify their camber to varying extents during their flight for better control of flight and greater efficiency. Some birds have an innately very extreme camber to their wings, so they have a very deep pocket in their wings, which of course, as we know, generates a great deal of lift. A good example of a bird that does this is something like this is a ruffed grouse here, something like a ruffed grouse, and so there's a reason that that birds like grouse have very exaggerated cambers. And that is because they are ground nesting birds. So think about what that means to the grouse. If you're a ground nesting bird, you are more prone to predators, right? Like you're on the ground where the predators are all the time. And in those instances, you need to be able to take off very, very quickly. Well, that high camber wing is extremely good at rapid takeoff and darn near vertical takeoff. And so these guys are built for escape. Their wing structure is built for escape. It is not an incredibly efficient wing for really anything else. It's not necessarily the most maneuverable wing. It's not good at prolonged flight in particular. It's not really good at that at all. But it's very good for an explosive, high energy takeoff that happens very, very quickly. So these birds are incredible with that. Um, some other ways we can tie in things like wing morphology and dealing with things like drag to uh, to these birds' natural history. You will see in birds like hawks that do a lot of soaring, you will see the wing tips. They're not overlapping each other. How we talked about in the feathers chapter, the feathers will overlap and they hold on to each other. We talked about all the structures that are involved in that. You'll see the tips of the wings, those feathers, those particular primaries, will be spread apart. And we talked about in that chapter, we talked about some different hypotheses for what might be the purpose of that. One of them, and the one that the chapter um, talks about here, is the idea that each one of these independent feathers acts like a tiny little airfoil at the tip of the wing, and what that does is it disperses the vortices that are created um, through the creation of bound circulation. It disperses them away from the tips of the wing, disperses them outward, and what that does is reduces drag and makes soaring more efficient. And then this is just a really cool a way that birds, and this is just pretty well birds in general, the birds deal with angles of high angles of attack, I should say it that way. If you look at this American kestrel here, you will see that it looks like it's giving you a thumbs up. Right? There's a feather sticking up on either side of each, on the top of each wing, let's say that, on the front leading edge of the wing. That's the best way to say it. What happens is, you can see this bird is at a high angle of attack right here. It's tilted this way, right? It's not like this, it's tilted this way. And this bird is either probably swooping down onto something, or it might be getting ready to land. I'm not really sure. The image comes from a Reddit post, and the link is there. You can go read the Reddit post. It might go into more detail. But that doesn't matter. The high angle of attack is what matters, and the two little thumbs sticking out. Those little thumbs are the alula feathers that we looked at in the feather chapter, the alula feathers. They can move those things around, and so they stick them up, and that disperses some of the drag away from the upper surface of the wing. And remember, at a high angle of attack, you generate a lot of drag. So dispersing some of that drag can be very helpful in controlling flight, particularly at slower speeds and high angles of attack. Again, one of the most common times you see this, if you watch something like an American kestrel landing, just about every time it lands, you'll see that it adjusts the alula as a part of that landing process. So this is a flight control mechanism for dealing with high angles of attack. All right, let's talk about wing loading. So wing loading is a fairly intuitive, I think, concept. And the idea here is that for any given body mass, if you have a greater wing surface area, you can produce more lift. Because the more body mass you have, the harder it is to lift yourself up, right? So if you have bigger wings with greater surface area, not just longer, but greater surface area, you generate more lift for the same body mass. It's kind of like, for maybe some of you that do workouts or things like that, or you're familiar with doing pull-ups, It's like how you don't see a lot of really massive people doing pull-ups, but you see these like tiny little individuals that can do like 30 pull-ups. Well, they have a lot less mass to lift, so it's much easier to lift that given mass. It's the same thing here. We are generating this lift, and that lift is based on uh, primarily on the size of the wings, right? We already talked about how a longer wingspan will produce more lift. So the overall surface area of the wing captures more total lift. If you are generating a set amount of lift and you have a larger body to pick up, there's a threshold at which your body can't pick up, or your wings can't pick up your body anymore, right? You're too heavy. So you can think of it in you can either think of it in terms of setting the body as a static weight and then adjusting the size of the wings, bigger wings generating more lift for the same body size, or set the wings at a certain size and change the body and change just the body size, and at some point you can't generate lift enough to even raise your body. Either way, no matter how you frame it, that idea is called wing loading. And so little bodies with big high surface area wings generate great amounts of lift. A bird like the magnificent frigate bird you see here generates a tremendous amount of lift due to very low wing loading. Because it's got a tiny body relative to the surface area of its wings. And for birds that do this, these are birds that tend to stay a lot in the air, for example. So they need to generate a lot of lift because they need to stay up in the air. Now, for the frigate bird in particular, it's beneficial because they eat fish and squid and crustaceans and things, and sometimes their food items can be fairly heavy. Because they have this low wing loading by default, they're able to carry more weight. If we go back to our example of doing pull-ups, it's like a smaller guy might even be able to load a weight on a belt and actually add weight to his body to make the pull-up harder and still be able to pull himself up. Whereas a bigger guy already has so much weight that even doing the pull-up at all is already challenging. So they essentially have more cargo space on the flight. Another thing this does is makes them kind of good at stealing food from other birds because it makes them a little more maneuverable. And so they can swoop in, grab food, and fly away quite easily. Okay, aspect ratio. Aspect ratio is what we get when we take the squared wingspan and divide it by the average wing chord. And we can see that here in this picture. Wing chord, average wing chord, and then the square of the wingspan. So if you have a long wingspan for the same wing chord, so if we set wing chord as a static value and extend the wingspan, what happens to the shape of the wings? They get longer and often kind of pointier, or more like a thin, long rectangle as we do this. And as long as we set that wing chord static and then we adjust wingspans, we can get skinnier and skinnier looking wings. Or in the opposite, if we hold that wing chord static, but we tighten up the wingspan, what happens is the wings start to look boxier and boxier. They get closer to a square, right? They get closer to a square. Or they get stubby looking. And so here you have that example with a great shearwater and a sharp-shinned hawk, where the great shearwater has these very elongate looking wings because the wing chord relative to the wingspan is quite short. And in a sharp-shinned hawk, the wing chord relative to the wingspan is closer to the same. It's not the same, of course, because that would be a perfectly square wing. It's not a perfectly square wing, but it's closer to the same. Aspect ratio is very, very important. High aspect ratio, like a shearwater here, has tremendous lift potential. They get a lot of lift for relatively little drag. That is an advantage of a high aspect ratio. On the other hand, these are not the most maneuverable wings. These birds are relatively poor in terms of maneuverability. Sharp-shinned hawks, on the other hand, with their lower aspect ratios, they're more blocky, squarish shaped wings, are less efficient in terms of lift-to-drag ratio. They produce more drag relative to lift. But as a trade-off, they are much more maneuverable, and they have a relatively strong takeoff as well. So there is a trade-off between lift and drag and the aspect ratio. It might become, with a little bit of thought, readily apparent as to why that might be important for a sharp-shinned hawk to give up some efficiency for higher maneuverability. Think about that. That might be something worth giving consideration to. So everything we've talked about so far is the wing as a whole, or a little bit about the remiges, but we haven't talked about the tail. We haven't talked about the rectrices, and they are important as well. The rectrices themselves generate lift. Actually, the body of a bird generates a very, very tiny amount of lift. It's not enough to get the bird to fly, of course, or even to lift it up a little bit, but it does technically generate a small amount of lift. But the tail generates lift and also, very importantly, reduces drag. In experiments, the optimal shape of the tail has been shown to be a triangle when the tail is fanned out. And this is probably what you think of when you think of a traditional tail shape in a bird. It's just a sort of triangle shape. And it's usually in a forked shape when the tail is folded up. And so this is a black-fronted tern. This is diagrams from your book, and you can see that it has that slight forked shape folded up. This is a very good shape for reducing drag. On the upper right there, we have a Reeves pheasant. We can see that its tail is incredibly long. It doesn't even come close to the optimal shape. It's about as far away from optimal as you can get. And of course, that just goes to show how important sexual selection is in creating these morphologies. That's right. And it kind of speaks a bit, in this case, to the handicap hypothesis that we talked about a couple chapters ago, where you see a bird that deviates very far from an efficient design in order to reproduce. So this picture on the left here is showing what happens as you remove the tail feathers from a bird, and it's a sequence of, so it's in an air tunnel, and you can see the airflow over the bird at three different situations, with the rectrices intact, the upper tail coverts intact, but the rectrices are pulled, and then everything is pulled. It's just got basically there's just a stubby butt left behind, and what you can see is the vortices of air coming off the bird get more erratic toward the back of the bird, and even over the top of the bird maybe to some extent, but definitely toward the back of the bird as you remove tail feathers. And the stream gets less. It's a less tight flow over the bird. It's showing that drag overall increases when you remove the tail. The tail helps pull the air toward the back of the bird, tight around the bird, and keep from having this great disruption of drag. Okay, so when we think about flying, there are probably a few different ideas you have about how birds fly. We're going to talk about a couple of those, and then we're going to move into some other stuff, and then we'll come back to some other concepts of how birds get around. The first is gliding. Gliding's pretty straightforward. Gliding is a controlled descent. Is a bird will hold its wings out and just slowly descend. They will hold their wings in such a way that they are creating a specific amount of drag so that they approach the ground or a perch or wherever they're trying to approach at a specific angle. The angle is determined by drag. The angle is a function of drag. Actually, it's an inverse function of drag. So as drag increases, the angle gets steeper, and this is the angle I'm talking about here. This is horizontal to a surface or to free stream velocity. Actually, you can think of it like that. Um, Here's drag, and drag is what's causing the bird to descend, and that descent angle is this angle right here. That's the glide angle, is an inverse function of the drag. So that's gliding. Flapping is probably ultimately the thing you think of when you think of birds flying. You think of a bird flapping its wings and it flies. Flapping is a way to overcome drag and to keep propelling the bird forward, right? And that is, in other words, it generates thrust. Um, so to go forward, you must generate thrust. Both of these are ways of doing that. I guess I should say that so far we've mostly talked about lift. Lift is getting up off the ground. We have to generate thrust too. We have to generate forward momentum to fly. These are the ways you generate forward momentum. You glide forward or you flap to generate thrust. So this thrust through flapping is a way to overcome drag. And you have two different types of velocity here that come from flapping. You have a translational velocity and flapping velocity. So the translational velocity is the velocity of the bird relative to the surrounding air. And the flapping velocity is the velocity of the wing during its oscillation. When you take those all together, the flapping and translational velocities, I'm having trouble talking now, you ultimately can determine what the incurrent velocity of air is relative to the wing. And so what does all of that mean? Well, here's translational and incurrent velocity coming in. And here's what you need to take from this. When we generate lift from this incurrent velocity, and this incurrent velocity is partially a function of this flapping velocity along with the translational velocity, we get lift, and that lift has two components. It's got, because you think you have to be kind of good at math to understand this. If you think about this is a vector, and it has two different magnitudes to create the vector going in this direction. It's got a horizontal magnitude or horizontal component, and it's got a vertical component to it. Right? The vertical component of this vector is supporting the weight of the bird. It's lifting the bird up. But there's this component, the horizontal. So this is the vertical component. I might have just misspoke there. The horizontal component is thrust. It's the part of this lift that's created from flapping and translational velocity that drives the bird forward. That is how birds move forward, by flapping. That's how birds generate thrust. There's a really, really interesting thing to think about when you think about flapping. And this is as true for this is true for any animal that has a similar mechanism to flapping. Um, so I'm going to pretend I'm a bird for a second because I think it's the easiest way to understand this. If I am a bird and these are my wings, and I make a downstroke, I generate a force. That force has a horizontal and a vertical component. One that creates lift, the vertical component, and one that creates thrust, the horizontal component. When I lift these wings back up, I will generate another force. But that force will be completely the opposite of the force I created on the downstroke. Well, that's a big problem because if I make the opposite force and all of the values are the same, all the quantities from that force are the same, then my net lift and net thrust is 0. So if we imagine I generate 1 mile per hour thrust, okay, um, on the downstroke. If I generate 1 mile per hour of the inverse of that on the upstroke, I've canceled out thrust. I make no thrust. That's a big problem. We have to find a way to overcome that problem, or else we don't ever move forward. Or for that matter, we're not able to even generate lift. At least through flapping. Flapping becomes pointless. How do birds do this? Well, they can do it in a whole bunch of different ways. What they can do is they can change the shape of the wing. In other words, by bending the wing slightly or changing the camber of the wing on the upstroke versus the downstroke. They can change the speed at which they do the upstroke and downstroke. They can change the orientation of the wing by angling the wing differently on the upstroke versus the downstroke. Any of those can reduce the opposition forces that are created during the upstroke so that there's overall a net positive generation of lift and thrust. That's how they do that. And so this picture on the right is depicting the flight, how should I say that, the pattern of wing movements throughout a full wing oscillation on this particular bird. I think it's a pigeon. I don't remember what the example in the book is supposed to be. It doesn't really matter. If you look, and this is at different speeds. This is slow, medium, and fast, we can call it. 6, 10, and 16 meters per second. If you look, in all cases, irrespective of the speed the bird is traveling, their wing flaps are not just these perfect linear up and down patterns. What these circles represent, these points represent a tracing of the tips of the wings throughout the oscillation. And so what you can see is the tips kind of come back and then reach back out again in this sort of circular like pattern. In other words, the upstroke and downstroke are not perfect mirrors of each other. It does not follow a nice linear path. The wing tip does not follow a nice linear path. And so I would almost think of it like using an oar, right? And using an oar, and it's more circular or figure eight-ish even. This is how we overcome the limitations that are created by the upstroke on the generation of lift and of thrust. Let's talk about power a little bit. So power is just a way of talking about the energy required to go, a certain unit of speed over, or over a certain amount of time. And flight is a very interesting thing to talk about in terms of power because if you look at the many, many species of animals in the world and how they move around and how much power it takes, flight is pretty much so the most power intensive activity an animal can do. You have a uh, constant battle with numerous forces at an extreme in an extreme situation. Um, and so let's take a look at this curve here. So this is the power consumption at various speeds. How much power do you have to consume to go various speeds? And it's interesting because it's an inverse parabola, so it's a U-shaped curve. In other words, at very very slow speeds, there's a massive amount of power consumption to stay at that speed. And at very high speeds, it's a massive amount of power consumption to continuously propel yourself at that speed. At the bottom of this curve, there are 2 points that are particularly interesting. The minimum power speed, and that is the speed at which you can stay in the air the longest. In other words, where you use the least total amount of power. Note that the minimum power speed is a little slower than the maximum range speed, but takes a little less energy. The maximum range speed instead is the speed at which you maximize the distance traveled for the amount of energy that is being consumed. So birds that want to stay in the air for a very long time want to travel ideally at their minimum power speed. If they're not concerned with distance, but just staying in the air, minimum power speed is the best. If a bird wants to travel at the optimum distance per unit energy, so say a bird in migration, for example, where it's just trying to get as far as it can every day until it gets to its migration grounds, it might want to travel at the maximum range speed. So these are the 2 different speeds that are probably the most important speeds to the vast majority of birds in terms of their strategies for choosing their flight speed. On the right, you have a diagram that shows these power curves for a few different species. There's one thing in particular to take from this, and that is that different birds with different morphologies have different power curves. They're all shaped like inverse parabolas, but they have different curves, which means, of course, the minimum power speed and maximum power speed for those species is also different. Something important to note here is this depicts hummingbirds, and your book goes into more detail on hummingbirds. Hummingbirds are one of my favorite groups of birds. They're really amazing creatures. Of all the birds, the flighted birds, hummingbirds are really the only species that has the capability to sustain flight in this part of the curve down here, right, where power consumption is very high, but velocity is very low. Hummingbirds are designed to hover, and that's exactly what it requires to hover. It requires a huge power output at very low velocities. Right, the bird's barely moving; it's trying to stay perfectly in place. And so the velocity is essentially zero, but the uh, power output is ridiculously high. Hummingbird's really the only bird that can do that. And there are, of course, many species of hummingbirds, and they that's what they do. They they hover, and they have to have a number of adaptations to deal with that. Some of them we're going to talk about when we talk about some of the anatomy and physiology stuff that's coming up. But in generally, what it requires is the ability to provide continuous aerobic respiration to the muscles, uh, the pectoralis muscle in particular, but the flight muscles, the supracorticeus muscles, another muscle that's involved in that process. And so they have to have adaptations such as higher heart rates and highly efficient respiration to provide that sort of energy production to those muscles. Okay, so we talked about energy now and power. How do we save energy? One of the major theme in evolution and a major theme in ecology is saving energy. Energy is everything. Harvesting energy, how efficiently using energy, saving it for when it's necessary. These are critical things for all organisms to deal with, because no energy, you're dead. You have to have energy. When I'm talking about energy, ultimately, of course, I'm talking about the unit of energy that we use, adenosine triphosphate, ATP. But how do we prevent ourselves from burning through all of that? That's the question. There's a few different ways that birds do it. They either do it through intermittent flight or they do it through soaring. Those are the two major ways. So these are the two forms of intermittent flight: flap bounding and flap gliding. They're not incredibly different from each other uh, in terms of what their ultimate goal is. Their ultimate goal is to save energy, but when they become appropriate is different. So let's take a look at this. So intermittent flight is just basically periods of brief rest in between bouts of flapping or otherwise using up energy in flight. So some birds, what they will do is they will do a hard downstroke that bounces themselves up. They might do a few. There might be a few strokes, and it bounces themselves up into the air with a really hard flap. And then they tuck their wings, and they let the momentum carry them forward without spending any more energy for a brief moment. And then they drop back down, and then they do it again, and they bounce up again. And so what this creates is a flight that looks like this. It looks like the bird is bouncing through the air. Really great example of a bird that does this is a pileated woodpecker. You will see this. Pileated woodpecker is a very large bird, and you'll see this huge bird bouncing across the sky, usually headed toward a tree. So that's flap bounding. Flap gliding is very similar, but instead of creating this bouncing thing, the bird flaps upward and then sticks its wings out and glides for quite a distance downward. And remember, glide distance, glide angle is determined based on drag. So the angle it's coming back down is going to be based on the drag. And it will glide to a certain height and then flat back up again and glide again. And so instead of a bouncing, you have a much more gradual up, gradual down, gradual up, gradual down. So these are applicable and efficient in different contexts, which is why different birds use them. And we can look at this in the context of velocity. If you look at the bottom picture here, we have a power curve. The black line is a sort of typical power curve that's that inverse parabola. And they all are, because all the power curves are going to look like that. But note that they aren't all sitting right on top of each other. If they were, there'd be no reason to do flap gliding or flap bounding, because they would all have the same power curve, but they don't. So if you look at the blue line there, that's flap gliding. Look at where it's most efficient. It's the most efficient part is down here in the trough again. It's most efficient at somewhat slower speeds than either of these, and the power difference is quite large between flap gliding and your standard flapping flight. But note that for flap bounding, that's not really the case at these lower speeds. It's less efficient to flap bound at lower speeds than it would be to just do a normal flapping behavior. And you can see that because the black line is lower on the power scale, power requirement scale, than the red line is. But what happens as we get to high speeds is suddenly, right here, um, it becomes the most efficient. Flat bounding overall starts to require less energy to produce those speeds. And so this, when you get up to these speeds in birds that travel at faster speeds, they tend to do this flat bounding behavior because it's more energy efficient. And at this point, it's right when you get to here. So when you get to here, it becomes a speed that is more efficient than standard flapping. Right here is more efficient than standard flapping, but maybe slightly less efficient than flap gliding. But once you break to whatever this velocity is, there's no actual scale down here, but this particular point of velocity, at this point, it is the most efficient, least power consumptive method of flight. Okay. One other way that we can be efficient aside from intermittent forms of flight is in soaring. And soaring is extremely efficient because it doesn't really require flapping at all. And there are at least 3 types of soaring that are listed by your book. Slope soaring, thermal soaring, and dynamic soaring. So when wind hits a hill or any other surface that has an upward slant to it, if wind hits that, it will be driven upward. And a bird coming out over that hill can catch that upward air and use that to generate free lift. And it will just hold its wings out and soar on that lift. It's just catching that wind and soaring on it. It's free energy essentially. They don't have to do anything. Ravens, crows, things like that, you'll see utilize these particular types of currents to generate free lift. The one you're going to be most familiar with, I think, is probably thermal currents. This is something that anyone who's ever driven down the road and paid any attention, or driven down a highway at least, and paid any attention to the birds around, has probably noticed. What will happen is the surface of the Earth gets heated differentially. Some spots on the Earth don't absorb and radiate heat at the same rate, and so you get pockets that are warmer than other areas, and the warmer pockets create a rising air current called a thermal. You will see vultures and sometimes hawks over the highway riding these thermals. Vultures are such a good example of this. I can't think of a better example of this. You will watch vultures if you really ever have just paid attention to what vultures do behaviorally. Right, they get in these big kettles a lot of times, and there might be a bunch of vultures all flying around, but they're all doing it. They just circle. They just keep going in circles. You might ask yourself, how the heck do they stay up that long without flapping their wings? They will stay up in the air all afternoon sometimes, and they don't flap at all. They ride upward thermal air currents that allows them to stay in the air for a really long time without burning any energy, which is pretty amazing. So that's how the thermal type of soaring works. The last one is dynamic soaring. Dynamic soaring is it's really cool. So in dynamic soaring, wind that get oceanic currents, wind currents, drive wind out over the ocean. And wind closest to the surface is kind of slow, and as you rise up above the surface of the ocean, such a distance, it gradually, the velocity increases. So the wind velocity increases. what birds like like albatross will do is they'll come along a wave trough where there's very little, excuse me, there's very little velocity, okay, air velocity at that point, and they come along that trough and they turn up toward the wind current. And so it starts to generate lift. Whenever you face directly into the wind, you generate the most lift because you're at that point you're facing into the free stream velocity directly. So you generate the most lift there. So that starts to pick the bird up above the wave crest. And so they launch themselves up above the wave crest and they ride this increasing velocity high into the air. And then they turn, they make a spin and glide back down. Okay, so you got to think of like a kind of like a corkscrew. They glide back down and then they catch the next wave trough and ride the wind back up into the sky again. This is how birds that stay out at sea that need to stay in the air for fairly long periods of time stay up. That's not to say these birds never land on the sea. They do. But when they are staying up for long stretches, that's how they do it. They come down into a wave trough. They ride they face into the wind. They ride the increasing velocities of the wind up above the wave crest and up into the sky, and then they turn and come back down into the next wave trough. And they just do this corkscrew pattern over and over and over again. They sort of are making loops as they fly. I think maybe that may be better or easier to understand than a corkscrew because it's not quite a corkscrew, but they make loops where they ride an air current, and then they drop back down and do it again. All right, I have to pretend to be a bird again for this slide. So there are three axes that birds need to control for flight stability, all positioned around the center of gravity. These are a little bit difficult to depict as a person because my center of gravity is not in the same place that a bird's center of gravity will be, but I'm going to try to depict these for you. So if I'm a bird, this is my roll axis. If I get blown to the side and tilt, I'm rolling. Obviously, that's bad. I don't want to spin clear over. Won't be flying for very long if that happens. The next is my yaw axis. That's if one wing or the other gets pulled back from the direction of my flight, outside of my flight, my vector of flight velocity. And then the last one is my pitch axis, which you can imagine as tilting forward or leaning back this way. So you've got roll, yaw, and pitch axes, and those have to be controlled. And birds have some cool ways of passively controlling these axes and making sure that they don't just go tumbling and rolling out of the sky. So, and vultures are a really good example for the first of these we're going to talk about, which is controlling roll. What happens with a vulture is they hold their wings in a dihedral position. Now this is this position. It's a V-shaped position, and a really good diagnostic for if you're watching birds far away in the sky and you're trying to figure out what they are. If they look like V's, at least around here, they're vultures. That's that dihedral wing pattern. As the dihedral pattern tilts, right, so if you imagine this finger and this finger are the wings, as it tilts because a roll, an air current, hits the side of our vulture here and tilts it, one wing will become closer and closer to parallel with the free stream velocity. It will be, as it becomes parallel with the free stream velocity, lift on that wing will be greater than it will be on this wing. And since lift is greater over here, it lifts the bird back up to its original position. That's how it works. As the bird tilts in one direction, the lift generated on one side automatically corrects. The other is yaw. Yaw again is this this kind of thing. So this passive stability mechanism works really similarly to the one we just talked about for roll, except for rather than based on lift, it's based on drag. And so when when a bird gets kicked out of its yaw angle from a gust of wind or something, it jerks the bird out of position. The bird will automatically be pulled back toward its direction of momentum. That's where its flight velocity is. By drag, what happens is as yaw tilt occurs, the opposite side of the tail begins to experience greater drag. That greater drag slows the bird on this side while the bird's going the same speed on this side, and it tilts the bird back into its flight trajectory. That's the blue line on that picture. So these are mechanisms that are passive. In other words, the bird doesn't put any energy into doing this. It just happens. And it's a really, really cool thing to think of. What a neat and efficient way to automatically correct stability. Obviously, if you throw these birds into a hurricane, these automatic flight stability mechanisms, they will be overcome. They work in a normal range of conditions. They don't work in all conditions, the most extreme conditions. All right. And so that takes us to the discussion question for this week. So it's choose a bird that was not discussed in this lecture or in a tag lecture and describe its flight in terms of its morphology, wing load, energy efficiency, or really any or some combination of the various concepts presented in this chapter. In other words, you need to do research on flight mechanisms and flight morphology and those things in a bird of your choice. I will tell you, because it's worth noting and understanding, that some of these scientific papers get very, very technical. These will be some of the, if you're finding the good ones, some of the harder things that you might read, because sometimes there's engineering ideas and concepts involved in this. There's often a lot of mathematical modeling. I'm not expecting you to become an engineer to write your discussion post, but I'm expecting you to get the greater understanding of the papers that you're reading and apply them to the writing. Additionally, you can use the book to talk about some of these ideas. So, for example, if you can't find anything about, let's say you pick greater sage grouse, you're not finding anything about camber in the greater sage grouse. Well, the book talks about camber, and you can apply the ideas of camber to that bird. You can no longer pick greater sage grouse because I just mentioned it in this lecture. But that's an example. Ultimately, you have to do a little research. Pick a bird, do a little research on that bird, see what's understood about its flight, and go from there. Now, for your responses, I had I think a really good question last week. There's some inconsistency in responses, and that's something that I need to address. For your responses this week, you must compare your species to the two discussion post species you're responding to. So I'll just flat out tell you how I expect you to respond so that inconsistency is no longer a problem. So in other words, I expect you to take your species in the context of its natural history and its flight biology and compare that to the two species that you're responding to. Okay. If you have any questions, of course, as always, reach out to me and I will try to get back to you as soon as possible.